Have you ever heard someone say, "Oh, I'm so hot, I think I have a fever"?
Yeah.
Yeah, so do they have a fever?
No.
Probably not. If they feel hot, they're too warm, the body's trying to cool off. Someone with a fever is putting on socks and wearing sweaters, and you feel hot, and they're saying it's cold in here because their body's trying to warm up, right? Okay. Questions on this? Yeah.
People who never get fever, is this process not working or other processes taking over?
What do you mean they never get fevers?
Like I've been sick a lot, but never.
You probably just haven't had a pathogen that's stimulated the production of these pyrogens. You know, two people can get the same infection and have really different responses from it. And
Maybe it's genetic. My parents
yeah, I don't know. I've never heard of people not having fevers, but certainly not everyone gets really sick from them. I bet you if we gave you a little tuberculosis, we could get you there. You just haven't had the right infection yet. We can solve that problem. All right, another molecule, because we're kind of thinking about molecules right now. We talked about these pyrogens, and we talked about all these chemokines and cytokines and inflammatory mediators. So these are all molecules that result in processes in your body. Another one that we mentioned briefly in that chart was interferon. And interferon is kind of a cool molecule. What it does is it's basically a way for a virally infected cell to warn its neighbors that there are bad guys in the neighborhood. Okay, so how does this work? This is some text for you, but I want to show you a picture. All right, so here's a picture of a cell. So here we go. This cell has gotten infected by a virus. You see how the virus got in? And it's producing viral nucleic acid, and now the cell's making new virus. So it's curtains for this cell. It's not going to survive this. Virus is going to kill it. But on its way out, it has one final thing that it does. It produces a molecule called interferon. The interferon is not going to help it. But when the interferon gets released from the cell, it binds to other nearby cells, and it binds to a receptor. And what this does is it communicates to this nearby cell that there are virus in the region. And it says, lock your doors and windows, right? And so what this cell does in advance of getting infected is it starts making antiviral proteins, and what it's able to do is break down virus that come into it, or sometimes block replication. Pretty cool, right? Does this work all the time? No. It's a strategy that helps maybe a little bit, right? I mean, if you've ever had a cold, you know that this isn't working 100% of the time because those viruses, and you get one in you and you still get sick. But this probably would, if you kept a fraction of your cells from dying, it would still prevent you from getting as sick. And also, a lot of what the innate immune system does is buys time for the adaptive immune system to get going. All right, so this is going to it's going to reduce losses by your body from the infection until your adaptive immune system can get deployed, which is sort of where we're headed here.
Is this a mechanism of a flu shot?
No.
No?
So when you get a flu shot, that's really adaptive immunity. Yeah. So we're getting there. I'm hoping to get partway to there today. All right, another process that I want you to know about that we're just going to touch on, because this is actually, we could do a whole lecture just on the complement system. It's a complicated complement. But you should know that in your blood, these molecules are made by your liver. There are about 30 molecules that are always circulating. And they're on Facebook, they're listening to music, they're doing nothing most of the time. But they're there, and this system is called the complement system because it complements your immune system. All right, it isn't your whole immune system, it's just sort of a complementary process. And what it does is when you get an infection, complement proteins can undergo a bunch of changes, and they actually begin to divide into pieces. And the different pieces of these proteins, as a result of an infection, can do three main things. And so this is what I want you to learn. So the complement system can, in the presence of pathogens, cause pathogens to break up, break down. Cytolysis means they're breaking cells, lysing cells, cytolysis. It can stimulate inflammation, and it can stimulate phagocytosis. So it's hard to explain this without going into more details, but again, because it's so complicated, there's either the really superficial way to explain it or the really detailed way. It's very hard to get into the middle. But what I want to point out is there are lots of molecules. C3 is a molecule that's one of these 30 complement molecules. And depending on how the complement system gets activated, it can be activated by antibodies binding to the bacteria. It can be activated by sugars that are present on the bacterial surface. And it can be activated by complement proteins themselves binding to the surface. So there's different ways for your complement system to get activated. Right? So you can make a phone call, you can send a text message, or you can go to their house and knock on the door. You see the idea here? So these are all just different ways to tell the complement system, get going. Once the complement system is activated by any of these pathways, these molecules start to break into a cascade. So this molecule C3 breaks into C3A and 3B. C3B then can break down into C5, and then C5 breaks into C5A and C5B. So they call it a complement cascade. One molecule breaks down into another, breaks down into another, breaks down into another. And I don't want you to have to memorize any of this. I just kind of wanted you to get this idea that it's triggering like a domino effect of these molecules. Some of these molecules, like C3A and C5A, actually are going to stimulate the release of histamine. And so this is going to increase inflammation because you're having more histamine produced. Some of these molecules, like C3b, actually bind to the outside of bacteria. Remember last time we talked about opsonization? And I mentioned it briefly, but I said if phagocytosis is a little bit, if you're the phagocyte and you like to eat chips, right? You can eat the chips, or you can dip the chips in guacamole first and then eat the chips. And so opsonization, when C3b binds to bacteria, it's like dipping the chips in guacamole. It makes the bacteria more delicious. And you can dip them in hummus, you can dip them in salsa, whatever your floats your boat. Cheese whiz, whatever you like. But if you did, this is a little bit like, it just basically coats the bacteria. These proteins coat the bacteria and make them they're just more yummy for the phagocyte to digest. It's going to enhance phagocytosis. And then the last major outcome of complement is actually these molecules forming a complex where they basically poke a hole in the bacteria and cause the bacteria to break apart. And when this happens, we refer to this as cytolysis. This is called the MAC, it's the membrane attack complex. So it's going to break down the membranes of these cells, these bacterial cells, and destroy them. So complement basically is different ways that these molecules, again, part of your innate immune system, your liver always is making these molecules, are always circulating. And if the pathways get activated by any of these mechanisms, all of these three things get stimulated in the body. Okay? So three things. Inflammation stimulates inflammation. It stimulates bacterial destruction by the membrane attack complex, and it stimulates phagocytosis. All of these are going to help your immune system get rid of some of these invading bacteria. Okay. Is there a question here? Oh no, what did I do to my clicker? Did I exit out? Apparently I did. All right, well think about it, because I'm about to give you this question. As soon as there it is. All right, opsonization stimulates what? All right, last chance to click in. We were just talking about this. Guacamole. All right. All right. So phagocytosis. Opsonization is, when we say opsonization, it's a general term for molecules that cover bacteria and make them more vulnerable to phagocytosis. I didn't do that. I meant to do this. I think I took our problems today. It's all user error. Okay, so, there's just so much that we could talk about. There's another part of the innate immune system that's fairly newly discovered, which are antimicrobial peptides. And so these are molecules that kill microbes directly. We see them in sweat now, sort of identifying this idea that you actually, when you sweat, you're producing peptides that have this antimicrobial effect, kind of like little disinfectants. One of the things you won't be surprised to hear is that people are actively doing research, trying to find ways to take these antimicrobial peptides and turn them into antibiotics. These are molecules your body already makes. We've discovered about 600 so far. And they are able to both kill microbes, and in some cases they can actually communicate with your immune system and inform it that there's an infection. One of the really nice things about these is that bacteria don't seem to develop resistance. And so that's nice, right? Especially if we can turn them into antibiotics. Here's an example of an antimicrobial peptide that what it's doing is going in and damaging the bacterial cell membrane. So the question is, can you use these as a drug that people take without hurting the people? There's a lot of research that needs to be done. This is an active area of work looking for antimicrobial peptides. All right, that's the innate immune system. There's a lot, right? First there's the keeping things from getting in you. Then if they get in, we said you have cells that help kill bacteria. We talked about phagocytosis as one of the ways they do that. And we talked about natural killer cells that kill bacteria a different way, right? We said that they use granzymes and perforins, right, to kill infected cells typically. Then we talked about processes. We said phagocytosis is a process. We said that inflammation is a process. Complement cascade is a process. And then among all these processes, there are molecules that are important to the process. So there are these cytokines like TNF-alpha. There are pyrogens that cause fevers. There's things like histamines and prostaglandins that are important in inflammation. So you're kind of thinking, if you can think categorically, maybe organizing this a little bit in your brain. Those are all ways that your innate immune system can deal with a pathogen before your adaptive immune system can get going. Okay, so I just talked about this a little bit, this idea that an antimicrobial peptide can be used to make an antibiotic. I said that one of the big advantages is that so far it doesn't look like your body develops or bacteria develop resistance to them. Oh, quicker question. Okay, my last slide too. Let's do this and then we'll talk a little bit about adaptive immunity. Which of the following are the main functions of the inflammatory response? Last chance? Okay. All right, so the inflammatory response, you guys did great. Mobilization of molecules and cells at the site of an infection or trauma. All right. So let's see what we can get through here with adaptive immunity in the time we have remaining. At least I can make the distinction for you between innate and adaptive immunity. All right, so your innate immune system, because you can never say it too many times, remember it's present at birth. You're born with it. It recognizes pathogens basically based on the fact that for, billions of years, your ancestors and you have been co-evolving with these pathogens and learning about each other. However, your body also is capable of making specific cells and molecules, the molecules are called antibodies, that recognize pathogens that you've seen before, so that once you get an infection, you can respond to it much more quickly the second time around. And so when we talk about adaptive immunity, we're referring to this ability of the body to respond to an infection and over time learn about a pathogen so that it can't make you sick if you get exposed to it again. Okay? So memories of T cells and B cells, T lymphocytes and B lymphocytes are the big cells that are important in the adaptive immune system. And so we have our memory T cell holding hands with E. coli saying, I will never forget you. Because once you've had an infection, these cells circulate in your system for years, sometimes for life, depends on how good the immune response was. All right, innate immunity is fast because you were born with it, it's present at birth, it's there. Right now, if you touch a door handle and get a cold in the next 20 minutes, your innate immune system is ready to go. Your adaptive immune system is slow, okay? So while this by 12 hours, all of these systems are mobilized. When you get exposed to a new pathogen, it's really, this says days, it says 5 days before you're making T cells and antibodies. And it may be true that at 5 days you've got some of this going on, but really it's a good 2 weeks. 10 days to 2 weeks before your adaptive immune system is kicked into high gear and is starting to really get a handle on an infection. Infections that kill you fast, one of the reasons they can succeed with that is because your adaptive immune system just doesn't have a chance to get going. So the goal of your innate immune system is really to hold an infection at bay long enough, to keep you alive long enough for your adaptive immune system to actually get you fully well again. And I would also argue that when you take antibiotics or antivirals, they're not getting rid of every bacteria, every pathogen in your body. What they're doing is they're helping your body get control of things by reducing the numbers until your adaptive immune system can really do the job of clearing out all of the pathogens that were made. So adaptive immunity is slow, it's specific. So once you have had polio, don't get polio. Once you've had a vaccine to polio, you should never get polio even if you're exposed. Once you've had the vaccine for measles, you should never get the measles because your body has seen measles. It saw it in vaccines, you didn't get sick, which is great. But it's seen it, so if it comes around again, you won't get sick from it. Okay? And it has memory, which is just what I was saying. Once your adaptive immune system has seen a pathogen, it remembers it. It's based on B and T lymphocytes, cytokines, and antibodies. So 4 main things. These 2 cells, these molecules that cells use to communicate with each other, and these molecules called antibodies. We divide the adaptive immune system into 2 branches, the humoral branch and the cellular branch. Humoral branch are things that happen outside the cells, things like antibodies, and the cell-mediated branch, or the cellular branch, are things like killer T cells, which are going to be the search and destroyers of infected cells and tumor cells in your body. Here's a picture here. So here's our extracellular antigen, like a bacterium, for example. These cells will recognize these and be stimulated by the adaptive immune system to make antibodies against those pathogens. Okay? So this is the humoral response. It's your body or the cells, the immune cells in your body, B cells in particular, recognizing a pathogen and making antibodies to protect you from it. The cellular branch involves T cells being activated to become cytotoxic T cells. So this T cell is actually becoming a killer cell that's going to recognize when a cell is infected and destroy it. It also is going to recognize abnormal cells. So just like natural killer cells, we said, could be an important way that your body kills tumor cells. Killer T cells, cytotoxic T cells are also in that they kill cells the same way, and are also important in controlling cancer in your body. Central to all of these processes is something called a helper T cell. And if you have learned anything about HIV, one of the things you may know is that HIV destroys helper T cells in your body. And helper T cells are needed for both the production of antibodies and the production of these killer T cells. So when you take out a helper T cell, you basically take out the immune system. It's sort of central command for the adaptive immune system. And that's why people get so sick from HIV if it's untreated, because their helper T cells are destroyed. All right. In the last 2 minutes, let's see how far we can get with antibodies. How many of you sort of feel like you know what an antibody is? Yeah, okay. So here's the bacteria, and you see that the bacteria has proteins on its surface? Each one of these is a protein. You see that? They're all the same protein, do you see? And then it's got some on the inside that are probably moving to the surface. Do you see how they have this, they're all the same protein here? All right, and so on this cell, on the surface of this cell, one of the things that can happen is that your body can make antibodies that recognize this bacteria. So you could say that, let's say this bacteria is the one that causes whooping cough, Bordetella pertussis. So if I gave you a vaccination, I could give you some of these antigens, and you would make antibodies against this bacteria. And if the bacteria got in your body, these antibodies would bind to it because they would recognize something called epitopes on the surface of these proteins. So this particular protein has 3 epitopes, 1, 2, 3. Proteins are large, and they have multiple different sites where an antibody might recognize the protein and bind to it. So each one of these proteins we refer to as an antigen. An antigen is something that stimulates antibodies to be produced. And then with an individual antigen, they can have multiple epitopes. So in this particular case, this antigen has 3 different shapes that an antibody could form a response to. So here's antibody A binds to the triangle epitope, antibody B binds to the circle epitope, but both of them respond to this particular antigen on the surface of, we said this bacterium is Bordetella pertussis. Okay. Yes?
So the epitope is a section of the protein that is recognized by the antibody.
That's right. So you have a protein that's part of the measles virus, and you might make 3 or 4 different antibodies against it. Because that protein's large, and so it may have several different pieces that antibodies recognize that are different. So epitopes are basically pieces of proteins that antibodies recognize. Okay. All right, so I'm looking at my watch here, when we come next time, we're going to finish talking about antibodies and then move on and talk about the humoral and the cellular immune response. And if we get to hepatitis C, that'll be great. If we don't get to hepatitis C, we will survive and we will cover it before the end of the semester. All right, so I'll see you guys on